Good morning. This is Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. So today we are going to start Chapter 11. Chapter 11 is going to involve in arenes and aromaticity. So in this chapter, we are going to show you what arene molecules are, what are the properties, and how do we name the different substituted compounds. What are the different chemical reactions? So that's our key points. So first of all, what are the arenes? Arenes are the molecules which composed of hydrogens and carbons. Arenes are the hydrocarbons, and they are also based on the benzene structural units. Your arene compounds have two key points. Number one, they are hydrocarbons. Number two, they are based on benzene structural unit. So this molecule, so you have a carbon 1, 2, 3, 4, 5, 6. 6 carbon, 6 hydrogens. This molecule is called benzene. If one of the carbon is replaced by CH3 methyl, you call it toluene. Commonly use the name toluene. The second molecule, toluene, the third molecule, if you have two benzenes, they share the two carbons. This molecule is called naphthalene. And then the benzene has lots of histories. So let's moving on to 1925. Michael Faraday is the first person who discovered the benzene and synthesized by another person in 1934. So the synthesis involved in benzoic acid, which you are going to place benzoic acid and calcium together, and then you heat it up. You produce the benzene and calcium carbonate. The benzene and the toluene were very important aromatic compounds. Benzene and toluene were called aromatic because they were derived from the aromatic plant extract. Benzenes can be isolated from coal tar for about 100 years, starting from 1945. Now you can obtain benzene from the petroleum resources. Currently, if I understand properly, your benzene has been used dramatically every year. So in the United States, we use 6 million tons of benzene and produce 6 million tons. The structure of benzene is very special. So a person called August Kekuli proposed the 6 carbon atoms of benzene are joined together in a ring in 1866. So he drew this structure. Carbon 1, 2, 3, 4, 5, 6 connecting to each other in a ring structure. Based on his reasoning, actually he provided 3 promises. Point 1, benzene has a formula C6H6, C6H6, and all the hydrogens of the benzene are equivalent to each other. The structural theory requires that there are 4 bonds of each carbon. Each carbon, you must have 4 bonds. So that's another important point. So what recently we figured out, if you have this structure of your benzene structure unit, so you have carbon double, single, double, single, double, single bonds, meaning you are going to have carbon double, single bonds inter-exchange. You are going to have 2 different formula. So you are going to expecting 2 different isomers for each of the Kekuli structure. So you have 2 formula, 2 resonance formula. In the real world, what we found, all this carbon hydrogen bond angle 120. All the carbon bond length is 140 picometer. Hydrogen carbon bond is 108, meaning hydrogen bond angle, hydrogen carbon bond strength, carbon bond strength and bond length, they're all identical. meaning your structure is not really this calculi structure. Actually, you are going to form a pi bond. So you use a circle to represent 6 pi electrons, which are provided by 6 carbons. So this different benzene structure, this 2 different calculi structures and one of the hybrid structure. So you can quantify the stability of your benzene. So what we normally use, we use the heat of hydrogenation. The heat of hydrogenation provides a mean for us to compare the stability of your benzene and the related hydrocarbons. For example, if you have this cyclohexene, you have 1 double bond. If you have dienes, 1,3-cyclohexadiene, you have this benzenes. Benzenes look like a triene. You have 3 double bonds theoretically. So how do we know which one is more stable? So this is what you are going to do. First of all, you are going to apply hydrogenation reaction. If this benzene reacted with your hydrogens, you can produce eventually cyclohexane. So this reaction requires platinum as a catalyst. You also need acetic acid in 30 Celsius, essentially room temperature. So this reaction must apply very high pressure, 2 to 3 atm. You are going to produce cyclohexane. If you have the cyclohexane, if you have your cyclohexane and dienes and benzenes, what are the stability? Which one is most stable? Based on our prediction, let's think about this way. If you have your cyclohexane, you have your cyclohexane, double bond, cyclohexane as our baseline. You want to convert benzene to cyclohexane. You want to convert diene to cyclohexane. You want to convert alkane to cyclohexane. You all have 6 numbered rings. For the first molecule, if this reaction occurs, you do need 120 kilojoules per mole. If you have this diene, theoretically you should need 240 kilojoules, but you do have about 9 kilojoules per mole, the heat of hydrogenation deduction. That difference between the expected heat of hydrogenation and the actual heat of hydrogenation is considered energy, considered resonance energy. For your benzene, if you based on this cyclohexane, so which is 120 kilojoules per mole in terms of the heat of hydrogenation, so you should need 360. However, in the actual reaction, you only need 208 kilojoules per mole, meaning this benzene is much more stable than what we think it is. So if you take a look, the real heat of hydrogenation is 108 kilojoules per mole. This 152 differences is called resonance energy. So the difference between the expected heat of hydrogenation and the actual heat of hydrogenation of benzene is 152 kilojoules per mole. This 152 kilojoules per mole is defined as the resonance structure of your benzene. Again, what does this mean? This means your benzene is a stable molecule. You don't really have a double single bond alternatively occur. It's not a triene. You are going to find a pi bond. We are going to show you about the molecular orbital theory related to 6 pi bonds. Also, your valence bond theory also provide the p orbital, which is not hybridized, will overlap. The unhybridized p orbital will overlap. So this is about the bonding in your benzene. The first structure showed you first A and B, so you showed you valence bond approach. Valence approach have all the carbons connected by sigma bond and also connected by pi bond. Pi bond is half occupied, half filled pi bond. They are going to overlap with each other. So this you form essentially is called pi bond. So you have 6 carbons, 1, 2, 3, 4, 5, 6 carbons. They have 6 pi bond. This 6 carbon benzene is a planar structure. The second important theory we call the molecular theory. This molecular theory concludes there are totally have 6 pi bonds are formed. 3 of them called the bonding orbitals, another 3 called anti-bonding orbitals. The anti-bonding orbitals have higher energy. The bonding orbitals have lower energies. What we also found, you have 6 electrons. Those 6 electrons is going to occupy the 3 bonding orbitals. These 3 bonding orbitals called pi 1, pi 2, pi 3. They are lower than your non-bonding atomic orbital for the carbon. And then you have anti-bonding orbitals, you call the pi 4 star, pi 5 star, and pi 6 star. These 3 different anti-bonding orbitals have higher energy and they are not occupied. In the reality, the overall energy of your benzene has been lowered compared with your carbon-carbon atom molecular orbital. So that's why your benzene is going to form a pi bond. So and then after you know these different compounds about the structure of your benzene, so how do you name the substituted derivatives of your benzene? So generally speaking, we are going to use your benzene as the parent. So compounds which contains a benzene ring, they are aromatic. The compounds named followed by your benzene ring will be containing benzene. So for example, the first one, you have a Br replace your hydrogen, you call the bromobenzene. You have a terbutyl which replace your benzene, you call terbutylbenzene. Similarly, you have NH2 which is called nitro, you call this molecule nitrobenzene. This is a mono-substituted. If you have di-substituted, tri-substituted, more than one substituent, you are going to name in the different system. We name 1,2, this 1,2 replacement, you call the 1,2-dimethylbenzene. This benzene also called also-xylene. O represent also. Also refers to the 1,2 substituents. If you have 1,3 substituents, you call the M-xylene. M-xylene represent meta. Make sure you use italic smaller m. This molecule, second one is 1,3-dimethylbenzene. This molecule also called M-meta-xylene. If you have 1,4-dimethylbenzene, so this molecule called P-paraxylene. 1,2, 1,3, 1,4 substituents. You also can call the ortho, meta, and para. This table 11.1, showed you common names and systematic names of lots of different commonly used substituted benzenes. I want to mention a couple of them. This first one, called benzoic acid, is a very important one. That's first of all, people mix it with a couple of calcium carbonate, you produce benzene. That's the first molecule you use. And then this styrene is commonly used monomer for your polymer, polystyrene. Polystyrene is the major chemical component for your styrofoam, so you can keep your food maintain the same temperature. And also you have another one, phenol. This is called phenol, called benzeno. Benzeno is a very important disinfectant from my understanding. However, inhalation of large quantity of phenol may harm your lung system, possibly neural system. The other ones like this aniline. So the other several different compounds, you may also learn them from your organic chemistry 2 in the next semester. We already essentially mentioned the nomenclature of your di-substituted benzene. Again, if you have 1,2 replacement, you call it ortho. 1,3 called meta. 1,4 called para. When you name it, make sure smaller O, smaller M, smaller P, italic it. So these couple names, I will leave it for everybody to further study. And then we are going to move on to the aromaticity. Some compounds, they are aromatic, like we just mentioned, benzene and its derivatives are aromatic compounds. How do you determine the aromaticity? Huckel's rule will be your Bible. You are going to apply Huckel's rule to determine the aromaticity. What do you mean by Huckel's rule? Huckel's rule states, in order to be aromatic, the compounds must be planar. In order to be aromatic, your compound must be monocyclic, fully conjugated polyenes. Number 3, in order to be aromatic, the compound must possess 4n plus 2 pi electrons. 4n plus 2 pi electrons. This n is a positive integer including 0. This n can be a whole number, has to be 0, 1, 2, 3, 4, 5, etc., etc. These compounds, the aromatic compounds, will have very special stability. The number of your pi electrons are corresponding to your 4n plus 2 will be 2, n is 0 will be 2, n is 1 will be 6, n is 2 will be 10, n is 3 will be 14, n is 4, 4 times 4 is 18, 18 plus 2, 18, etc., etc. Again, the pi electrons corresponding to 4n plus 2 can be calculated based on n equals 0, 1, 2, 3, 4, etc., etc. If you have the number 4, 8, 12, 16 is the number related to 4n. This rule you call the extended Huckel's rule. Extended Huckel's rule showed you the system is planar, the system is monocyclic, fully conjugated polyene, but possess only 4n pi electrons. This rule, extended Huckel's rule, indicates the anti-aromaticity. This anti-aromaticity is the molecule is going to be destabilized. So these anti-aromatic polyenes are specifically stabilized. So how do we plot this different energy? How do you determine which one is aromatic, which one is not, and why they are aromatic? Why aromatic compounds has been stabilized? On the other hand, your non-anti-aromatic is not stabilized, it's destabilized. What's the reason? We can use the Frost cycle to represent your pi bonds. Frost cycle is a diagram. This Frost cycle shows the relative energy of the pi orbitals of your cyclic conjugated system. This cyclic conjugated system must be the polyenes, at least dienes, such as butadiene. When you draw the Frost cycle, you need to follow 4 key steps. First step, you are going to draw a circle. Second step, you are going to draw a regular polygon inside the circle with one of each corner at the bottom. You are going to allow each point where the corner of your polygon to touch the circle. Therefore, that point touching corresponds to pi electron energy orbital. Possibly you're already confused. We are going to show you in the next slide. And then you are going to cut your circle into half. Therefore, the middle of the circle defines the non-bonding orbitals. Those non-bonding orbital energy level is going to be expressed by your circle middle levels. And then the bonding orbital energy going to be below the middle of your circle. The anti-bonding orbital energy level will be above your middle of the circle. So let's take a look. For example, this is cyclobutadiene. You have cyclobutadiene. You are going to draw a circle, and then you are going to cut the circle into half horizontally. The middle, this middle represents your anti-bonding. Below is your bonding orbital energy level. Above is anti-bonding orbital energy level. So anti-bonding higher in energy, bonding orbital lower in terms of energy. So butadiene, you totally have 4 carbons. You draw a polygon, it's a 4-numbered ring, it's a diamond. Each of these points from your polygon touches your ring, represent your energy of that related orbital. So that's called the Frost cycle. And then this Frost cycle, you have 4 pi electrons. At 4 carbon, each carbon provide 1 electron, 4 pi electrons. 2 of them is going to be occupying the bonding orbital. 2 will be occupied non-bonding orbital. Your bonding orbital will be unoccupied, empty. If you have your benzene, again, you're also going to draw a circle, and then you are going to cut it into a half, into 2 of the halves, and then you are going to draw a polygon. So you have the hexagonal structure, 6-numbered ring. Each of the point of your hexagon, your polygon, hexagonal polygon is going to touch your circle. Each of these touching, that one represents the orbital energy level. So totally you have 3 bonding orbitals, pi 1, pi 2, pi 3, and a pi 4 star, pi 5 star, pi 6 star. So these 3 above the middle is considered anti-bonding orbital. Energy increases. These 3 below this middle called bonding orbital. What we found, all the 6 pi electrons from your 6 carbons, they are located in the bonding orbitals, pi 1, pi 2, pi 3, and paired. So you can see, so due to the occupation of your electrons into the bonding orbital in the molecular orbitals, so your benzene subject to special stabilization. And your third example is a cyclooctatetraene. You have 1, 2, 3, 4, 5, 6, 7, 8 carbons. You form 4 double bonds. So totally, this one you have 8 pi electrons. You follow 4n rule. This benzene, you follow 4n plus 2. So n is 1, 4 times 1 plus 2, which is 4. This cyclooctatetraene, you have 8 electrons totally, pi electrons. So you are going to do the same thing. You draw a circle, you cut the circle into half. This is your middle level. And then you are going to draw a polygon. A polygon, you have 8-numbered ring. What my suggestion for you when you draw this, draw a circle first and cut it into half, and cut it into quarters, and further cut it into 1/8 and 1/8. So that way you have 8 points. What we found, 2 points located in the middle ring, meaning these 2 orbitals are the non-bonding orbitals. You have 3 bonding orbitals, you have 3 anti-bonding orbitals. 80 electrons will occupy the bonding and the non-bonding. You have 6 in your bonding orbitals. You have 2 in your non-bonding orbital. This non-bonding orbital occupation refers to the delocalization. So what we found, your benzene molecule is much more stable compared with other ones. So again, to emphasize, the benzene has 3 filled bonding orbitals. So your 6 pi electrons, they are all they are filled in the bonding with the paired electrons. Therefore, the benzene is stabilized. On the other hand, your cyclobutadiene and the cyclooctatienes both have 2 partially filled non-bonding orbitals. You see, non-bonding orbitals, they are partially filled in. And your non-bonding orbital partially filled in, so which resulted in a special instability. So meaning this partially unstable, partially occupied non-bonding orbital will attract to some other electrons, meaning these non-aromatic compounds may have special reactivities. So I think I'm going to stop it for now, and followed by we are going to study the different reactions of your arenes. Particularly, we are going to study the SN1 reactions of your benzylic